What if I told you the universe has been whispering its secrets to us all along, not in words, but in patterns so perfect they border on the divine? Picture this: every spiral galaxy, every swirling nebula, even the tiniest quantum particles, all moving in sync with an invisible choreography. This isn't poetry. It's the startling truth hidden in the fabric of reality. Cosmic symmetry isn't just a pretty idea. It's the silent architect of everything, from the birth of stars to the behavior of light itself. And yet, we've only just begun to decode its language. Think about the last time you marveled at a snowflake's intricate design or the hypnotic swirl of a sunflower's seeds. Those aren't accidents, they're echoes of the same mathematical harmony that shapes the cosmos. But here's where it gets wild. Scientists are now uncovering symmetries so profound, they challenge the very foundations of physics. What if black holes aren't chaotic voids but mirrors reflecting hidden symmetries we've never noticed? What if the key to unifying Einstein's relativity with the quantum world has been hiding in plain sight, written in the universe's flawless geometry? This is where our journey begins. Over the next 28 revelations, we'll peel back layers of cosmic mystery, each more astonishing than the last. You'll discover how symmetries govern forces we once thought were random, how they might explain the universe's missing pieces, and why these patterns could be the Rosetta Stone for a new era of physics. So buckle up, because by the time we're done, you won't just see the universe differently, you'll feel its rhythm in your bones. Let's rewind to the very beginning, the moment the universe flickered into existence. The Big Bang wasn't just an explosion of chaos. It was a masterpiece of symmetry, a near-flawless equilibrium where energy and space stretched outward in perfect harmony. Picture a balloon inflating uniformly in every direction, or a rippleless pond disturbed by a single, pristine drop. That's the symmetry we're talking about, a state so balanced, even the slightest deviation from it had cosmic consequences. In fact, without that minuscule imperfection, that 1 in a billion asymmetry, matter as we know it might never have formed. Stars, planets, even us. We exist because symmetry broke just enough to let particles clump together. But here's the mind-bending part. That primordial symmetry didn't vanish. It left fingerprints. Scientists scanning the cosmic microwave background, the afterglow of the Big Bang, have detected faint patterns, like whispers of that initial perfection etched into the fabric of space-time. These aren't random fluctuations, they're mathematical echoes, subtle clues that symmetry didn't just set the stage, it might still be pulling strings behind the scenes. Think of it like a grand symphony where the opening chord never truly fades. Even now, 13.8 billion years later, the universe hums with remnants of that first flawless note. What does this mean for physics, everything? If we can decode these echoes, we might unlock why the cosmos favors certain shapes, why forces like gravity and electromagnetism behave the way they do, even why time flows in one direction. Symmetry isn't just a relic of the past, it could be the universe's operating manual, written in a language we're only beginning to understand, and the most thrilling part. This is just the first revelation. The deeper we look, the more symmetries we find, each one a breadcrumb leading us closer to the heart of reality itself. Now imagine stepping through a cosmic looking glass into a world where everything you know is flipped, where time runs backward like a film reel in reverse, where particles dance to rules that seem written in a mirror. This isn't science fiction, it's the mirror universe hypothesis, one of the most tantalizing ideas in modern physics. What if our universe isn't alone, but paired with a hidden twin, a shadow realm where the laws of physics play out in perfect inversion? At first glance, it sounds like fantasy, but the math behind it is startlingly elegant. Symmetry isn't just about balance, it's about reflection, and this theory takes that principle to its ultimate extreme. Take neutrinos, those ghostly particles that pass through you by the trillions every second without a trace. Recently, scientists noticed something odd. These particles might be flickering between our universe and their mirror counterparts, like whispers crossing a dimensional divide. If true, this could solve one of cosmology's biggest mysteries: dark matter, that invisible stuff making up 85% of the universe's mass. It might not be some exotic particle we haven't found yet. It could be ordinary matter from the mirror universe, bleeding into ours just enough to tug at galaxies with its gravity. Picture two soap bubbles pressed together, their surfaces barely touching. We can't see the other bubble, but we feel its presence in the way ours bends and warps. Here's where it gets even wilder. The mirror universe wouldn't just mirror matter, it would mirror time itself. In that world, entropy might decrease instead of increase, meaning cause and effect could run in reverse. A cup of coffee would reassemble from spilled droplets. Shattered glass would leap back into place. To an observer there, our universe would seem just as bizarre. This isn't mere speculation. Experiments are underway right now to test for mirror neutrinos using ultra-sensitive detectors buried deep underground. If they find them, it would be like catching a glimpse of our cosmic reflection for the very first time. But why would nature need a mirror universe at all? The answer might lie in symmetry's deepest role, as a kind of cosmic error correction. Just like a painter balances light and shadow, the universe might use mirroring to preserve perfect mathematical harmony. Any asymmetry in our world, like the mysterious dominance of matter over antimatter, could be offset by its opposite in the mirror realm. It's as if the cosmos, in its infinite wisdom, split reality in two to keep the books balanced. And if that's true, then every star, every atom, every law of physics we've ever known is just half of a much grander equation. The implications are dizzying. Unifying these mirror worlds could rewrite the standard model of particle physics, bridging gaps that have puzzled scientists for decades. It might even explain why our universe seems oddly fine-tuned for life, because the mirror universe is fine-tuned in reverse, cancelling out the irregularities we can't explain. This isn't just about finding new particles, it's about discovering that reality is far vaster and more interconnected than we ever dreamed. And the most thrilling part, we might be on the verge of proving it. With each neutrino detected, with every anomaly measured, we're not just peering into the unknown, we're knocking on the mirror's surface, waiting to see what knocks back. Einstein envisioned space-time as a smooth, unbroken fabric, a cosmic stage where gravity warps and bends like a trampoline under a bowling ball. But what if that elegant simplicity is just an approximation, like mistaking a finely woven tapestry for a blank sheet from a distance? Beneath the surface, reality might be far stranger, a shimmering fractal where patterns repeat infinitely, from the vast expanse of galaxy clusters down to the frenetic dance of quantum foam. Imagine zooming into a snowflake and discovering its jagged edges are made of tinier snowflakes, which themselves contain even smaller versions, ad infinitum. That's the radical idea gaining traction among physicists. The universe may not just have symmetry, it might be symmetry, built from self-similar echoes at every conceivable scale. This isn't just poetic speculation. The math behind fractal space-time could solve one of science's greatest headaches, the clash between quantum mechanics and general relativity. Quantum particles jitter unpredictably, defying Einstein's orderly curves. But if space-time has a fractal structure, those quantum fluctuations might not be chaos at all. They could be the universe operating on a deeper, more intricate rhythm. Picture a musician playing a single note, then realizing it's actually a symphony of harmonics too subtle to hear at first. Fractal geometry might be the hidden harmony underlying both the quantum and cosmic scales, a Rosetta Stone translating between two languages we thought were incompatible. Evidence is already emerging from unexpected places. When scientists analyzed fluctuations in the cosmic microwave background, the oldest light in the universe, they found eerie echoes of fractal-like patterns, as if the Big Bang left behind a cosmic fingerprint with infinite layers. Even black holes, those ultimate paradoxes of physics, might hold clues. Some theories suggest their event horizons aren't smooth boundaries but fractal surfaces, bristling with quantum-scale turbulence. If that's true, then the key to Hawking radiation, the mysterious glow that lets black holes evaporate, might lie in understanding how these fractal layers interact. The implications are staggering. A fractal universe would mean there's no true, smallest or largest scale, just endless iterations of the same geometric theme. Particles we once called fundamental might be knots in space-time's infinite weave, and the expansion of the cosmos could resemble the branching growth of a fern unfurling in hyperdimensions. Even time itself might not flow smoothly but in discrete, self-repeating steps, like the frames of a never-ending animation. But here's the real kicker. If space-time is fractal, then every law of physics we've ever written might just be a rough draft, an approximation of a far grander, more intricate truth. It's like spending centuries studying shadows on a cave wall, only to realize they're cast by a multidimensional sculpture spinning in directions we can't yet perceive. The hunt for this fractal geometry isn't just about rewriting textbooks. It's about stepping into a universe where the very fabric of reality is more alive, more layered, and more astonishing than we ever dared to dream. Two particles born from the same quantum event, separated by light years of empty space, yet when you tweak one, its partner instantly responds, as if no distance exists between them at all. This eerie connection, quantum entanglement, has baffled scientists for decades. Einstein famously called it spooky action at a distance, dismissing it as impossible. But here's the twist: entanglement isn't just real. It might be the universe's way of revealing a symmetry so profound, it stitches space together like invisible thread. Think of entangled particles as cosmic twins, each holding one half of a shared secret. Measure one's spin as up, and its partner will always be down, no matter if they're a millimeter or a galaxy apart. This instant correlation defies our everyday intuition, like flipping a coin in New York and knowing without delay that another coin in Tokyo landed on the opposite side. For years, physicists assumed this was mere coincidence, a quirk of quantum math. But new research suggests something far more radical. Entanglement might be evidence of a hidden symmetry woven into space-time itself. Imagine space as a vast, interconnected web. What we perceive as empty void could be buzzing with microscopic threads linking every point in the universe. Entangled particles aren't communicating faster than light. They're not communicating at all. Instead, they're tapping into this pre-existing symmetry, a kind of cosmic blueprint where their fates were always aligned. It's like two dancers on opposite sides of a stage, moving in perfect sync, not because they're signaling each other, but because the choreography itself demands it. This idea turns traditional physics on its head. If entanglement reflects a deeper symmetry, then space isn't just a passive backdrop, it's an active participant, resonating with connections we're only beginning to detect. Some theories even propose that entanglement could enable shortcuts through space-time, like wormholes forged from pure geometry. Picture folding a piece of paper so two dots touch. The symmetry of the fold makes distant points neighbors. Similarly, entangled particles might be exploiting hidden folds in the fabric of reality. But here's the real bombshell. If we can harness this symmetry, it could revolutionize communication. Quantum networks already use entanglement to create unhackable encryption. But what if we could leverage these space-time threads for instant data transfer? The catch: any attempt to send a message would unravel the entanglement, like cutting the very thread you're trying to use. Yet some scientists speculate that advanced civilizations might have cracked this puzzle, embedding information in the symmetry itself rather than the particles. The implications stretch beyond technology. If entanglement is rooted in cosmic symmetry, it could explain why the universe appears so finely tuned for life. Just as entangled particles share a hidden bond, every atom in existence might be subtly linked by an underlying harmony, a silent symphony guiding the cosmos toward complexity. We're not just observers of this symmetry, we're expressions of it, stardust woven into the same grand pattern that connects electrons to galaxies. And the most exhilarating part: we're just starting to listen to the music. The spiral arms of the Milky Way don't just swirl randomly, they unfurl with the same precision as a nautilus shell, each curve obeying an ancient mathematical rule known as the golden ratio. 1.618. This number, revered by artists and architects for millennia, isn't just pleasing to the eye. It's etched into the cosmos itself, from the whirlpool galaxies spinning in distant voids to the orbital dance of planets around their stars. Coincidence? Not likely. Scientists are now uncovering something extraordinary. This ratio might be the hidden scaffolding of the universe, a silent architect shaping everything from the vast to the infinitesimal. Take Saturn's rings, those dazzling bands of ice and dust. Their gaps aren't scattered haphazardly. They follow divisions that align almost perfectly with the golden ratio. Or consider the way galaxies cluster across the cosmic web. Their distribution isn't random but mirrors the same fractal patterns seen in fern fronds and river deltas. Even the very fabric of space-time, when modeled at quantum scales, appears to vibrate in ratios that echo this universal constant. It's as if nature has a favorite blueprint, one it revisits again and again across scales we're only beginning to map. But here's where it gets truly mind-bending. New simulations suggest the golden ratio isn't just a passive observer in cosmic evolution, it might actively drive it. When physicists modeled the growth of galaxy clusters using this ratio as a foundational rule, something remarkable happened. The virtual structures that emerged matched real-world observations with uncanny accuracy, as if the universe had been solving an equation we'd just begun to write. This isn't numerology or wishful thinking, it's mathematics revealing a language deeper than we imagined. Why would the cosmos favor this specific number? The answer might lie in efficiency. The golden ratio represents a perfect balance between expansion and restraint, a sweet spot where energy distributes itself without waste. In spiral galaxies, it allows stars to orbit without collisions while maximizing gravitational stability. In planetary systems, it could explain why certain orbital resonances, like the rhythmic dance of Jupiter's moons, repeat with such harmony. Even black holes, those chaotic maelstroms, seem to emit gravitational waves in frequencies that approximate the ratio's harmonics. The implications stretch beyond mere curiosity. If the golden ratio truly governs cosmic growth, it could redefine how we search for extraterrestrial life. Imagine tuning our telescopes not just for water or oxygen, but for worlds orbiting in golden proportions, systems where stability and complexity naturally flourish. It might even reshape our understanding of the multiverse. If other universes exist, do they too hum to the same mathematical tune, or is ours uniquely attuned to this ratio's magic? Yet the most profound revelation isn't just about numbers, it's about connection. The same ratio that guides galaxies also appears in the double helix of DNA, the branching of trees, even the rhythm of human hearts. This isn't just symmetry, it's a whisper of unity, a hint that the cosmos and life itself might be threads in the same grand tapestry. And if that's true, then every time we gaze at a spiral galaxy or a sunflower, we're not just seeing beauty. We're glimpsing the universe's deepest secret, that all things from the smallest cell to the largest supercluster are bound by the same invisible hand. Stephen Hawking shook the foundations of physics when he declared that black holes don't just swallow matter, they erase information from the universe itself. It was a cosmic horror story. Toss an encyclopedia into a black hole, and its knowledge would be scrambled into meaningless noise, lost forever. For decades, this idea haunted scientists, violating a sacred principle of quantum mechanics, that information can never truly vanish. But what if the answer to this paradox has been hiding in plain sight, encoded in the very symmetries that shape black holes? Recent breakthroughs suggest these cosmic vacuums aren't the ultimate shredders we once feared. Instead, they might be meticulous archivists preserving information in ways so subtle, we've only just begun to detect them. Imagine a black hole not as a chaotic pit, but as a hall of mirrors where every particle swallowed is reflected, twisted, and stored in geometric patterns woven into the event horizon. This isn't science fiction, it's the holographic principle in action, the radical idea that all the information falling into a black hole gets imprinted on its surface like a celestial fingerprint. Here's how it works. When matter crosses the event horizon, it doesn't just disappear. Its quantum states, the spin of an electron, the charge of a proton, get smeared across the black hole's boundary in a fractal-like code. Think of it like burning a book. The pages vanish, but the ash and smoke still carry traces of the ink's arrangement. In this case, the ink is quantum entanglement, the same spooky connection that links particles across space. The black hole's surface becomes a sprawling ledger, with every infalling atom locked in a symmetrical web of relationships, but the real revelation. These symmetries might resolve Hawking's paradox without rewriting physics. When a black hole evaporates via Hawking radiation, it doesn't just leak random energy. That radiation could be subtly imprinted with the original information, like a radio signal encrypted in static. The key lies in the black hole's hidden geometry, its ultra-precise symmetries acting as a cosmic decoder ring. Picture a lockbox with a combination known only to the universe. As the black hole shrinks, its symmetries unscramble the information, releasing it back into the cosmos like a message in a bottle. The implications are staggering. If true, this means black holes aren't the universe's trash compactors, but its most sophisticated hard drives, even more astonishing. The same symmetries might govern the birth of new universes. Some theories suggest that when a black hole collapses, its information doesn't vanish. It becomes the seed for another cosmos, a branching reality where every fallen star is reborn. It's as if black holes are cosmic librarians, cataloging existence itself in geometries we're only beginning to decipher. Yet the most thrilling part isn't just solving a 50-year-old paradox. It's realizing that symmetry isn't just a feature of the universe, it's the glue holding reality together. From the tiniest quark to the mightiest black hole, nothing is ever truly lost. It's simply transformed, echoing in the hidden patterns that bind space, time, and information into one seamless whole. And if we can learn to read those patterns, we might finally unlock the universe's deepest ledger page after page, written in the language of perfect symmetry. Time crystals sound like something ripped from a science fiction novel, structures that don't just exist in space, but pulse rhythmically in time itself, like a heartbeat woven into the fabric of reality. Unlike diamonds or snowflakes whose patterns repeat in 3 dimensions, time crystals break the mold by oscillating in a 4th dimension, time. Picture a clock that ticks forever without any energy input, or a dance where the steps repeat perfectly, not because the dancers practice, but because the music itself demands it. This isn't hypothetical. In 2016, scientists stunned the world by creating the first time crystals in the lab, proving that matter can indeed organize itself into this bizarre, time-bound symmetry. How do they work? Imagine pushing a child on a swing. Normally, the swing moves at the same rhythm as your pushes, a one-to-one relationship, but time crystals defy this logic. Push them at one frequency, and they respond at a slower one, like a swing that sways back and forth twice for every single nudge you give it. This odd behavior emerges from quantum entanglement, where particles lock into a collective rhythm that resists external influence. It's as if the crystal remembers its own beat, immune to the chaos around it. And here's the kicker. This oscillation happens without energy loss, meaning time crystals could, in theory, pulse forever, a tantalizing whisper of perpetual motion. But before you imagine infinite energy machines, there's a catch. Time crystals don't violate thermodynamics because they don't produce usable work. They're more like cosmic metronomes, keeping perfect time without powering anything else. Yet their very existence rewrites the rules. Traditional matter settles into equilibrium, like hot coffee cooling to room temperature. Time crystals, though, never settle. They're permanently out of equilibrium, dancing to a quantum tune that never fades. This discovery has sent shockwaves through physics, suggesting that there might be entirely new phases of matter hiding in plain sight, governed by temporal symmetries we've only begun to explore. The implications stretch far beyond theory. Time crystals could revolutionize quantum computing. Their stable, fault-resistant rhythms might serve as perfect clocks for qubits, the fragile building blocks of quantum processors. Imagine a computer that never loses track of time, where information stays coherent far longer than ever thought possible. Or consider deep space navigation. Time crystals could provide ultra-precise timing for spacecraft, unaffected by the cosmic noise that scrambles conventional atomic clocks. But the most profound revelation lies in what time crystals say about the universe itself. If matter can lock into perpetual motion without energy, could the cosmos harbor other exotic phases hiding in the quantum foam? Are black holes or neutron stars flashing with temporal symmetries we've yet to detect? Time crystals hint that reality might be far richer, far stranger than our textbooks ever suggested. They're not just a new kind of matter, they're a window into a hidden layer of existence where time itself becomes a canvas for nature's most elusive art. Picture your entire existence, every memory, every sensation, even the screen you're staring at right now, as nothing more than a shadow. Not a metaphor, but a literal projection, like a movie playing on the curved wall of an immeasurably vast cosmic theater. This is the holographic universe theory, and it's not just wild speculation. Some of the brightest minds in physics now suspect that our three-dimensional reality might be an illusion, a hologram cast from information etched onto a distant two-dimensional surface. Let's break this down. Imagine slicing open a black hole and spreading its contents flat, like peeling an orange and pressing its skin onto a table. Astonishingly, all the information about what fell inside every atom, every photon, would fit perfectly onto that flattened surface without losing a single detail. It's as if the black hole's three-dimensional bulk is just a convenient illusion, while the real data lives on its two-dimensional boundary. This isn't science fiction. It's the holographic principle, a radical idea born from the math of string theory and quantum gravity. And the implications are staggering. If a black hole's interior can be encoded on its surface, why not the entire universe? Evidence is mounting in unexpected ways. When physicists study the cosmic microwave background, the oldest light in the cosmos, they've detected faint pixel-like patterns, as if the universe itself has a resolution limit, just like a digital screen. Even more compelling, calculations show that the maximum entropy, the total information capacity of any region of space, doesn't scale with its volume, as you'd expect, but with its surface area. It's as if reality is a painting, and the canvas isn't inside the frame but stretched tightly around its edges. But how could a flat surface conjure a world as rich and textured as ours? Think of a credit card hologram. Tilt it, and the flat sticker seems to contain a three-dimensional eagle or globe. Now imagine that sticker is the edge of the universe, and the hologram it projects is everything you've ever known. The math suggests that what we perceive as depth, as solidity, might be emergent, a cosmic magic trick where collective information on a distant boundary creates the illusion of volume. Even time itself could be part of the illusion, a secondary effect of how that underlying data interacts. Here's where it gets even wilder. If the holographic principle holds, it could solve one of physics' biggest headaches, the conflict between quantum mechanics and Einstein's gravity. Quantum particles buzz with uncertainty, while gravity sculpts space-time with smooth precision. But if gravity itself emerges from quantum data on a 2D surface, like steam rising from hot water, these two theories might just be different perspectives of the same deeper truth. It's like realizing that the war between waves and particles was never a war at all, just shadows of a single, unified reality we're only now learning to see. So what does this mean for us? If the holographic principle is correct, then free will, consciousness, even the passage of time might be secondary phenomena, epic side effects of information processing on a cosmic scale. You're not just in the universe, you are the universe, a fleeting pattern in an infinite data stream. And the most humbling thought of all, if this is true, then somewhere on the farthest edge of existence, there's a version of you written in code simpler than binary, a whisper of information that, when projected through the lens of reality, feels sunlight, hears music, and wonders against all odds if it's truly alone. For years, supersymmetry was the brilliant theory that promised to unite all the forces of nature, then became the one that seemingly refused to show up to its own party. Dubbed SUSY by physicists, it proposed that every known particle has a hidden twin, a superpartner with unique properties that could explain everything from gravity's weakness to dark matter's invisibility. Yet after decades of searching, colliders found nothing. Critics declared SUSY dead. But now, in a twist worthy of a cosmic thriller, strange bumps in the data from the Large Hadron Collider suggest we might have been too quick to bury it. What changed? Those elusive superpartners might not be missing. They could just be heavier than anyone predicted. Imagine hosting a dinner party where your guest arrives fashionably late, long after you'd assumed they'd stood you up. That's the scenario unfolding in particle physics. Recent anomalies in proton collisions reveal unexpected energy spikes, like footprints of something massive briefly flickering into existence before vanishing. These aren't random noise. They line up eerily well with tweaked SUSY models where superpartners are just beyond our current energy reach, waiting to be unmasked by more powerful collisions. Here's why this matters. If supersymmetry holds, it could solve two of physics' greatest puzzles in one swoop. First, dark matter. The lightest superpartner, often called the neutrino, would be stable, invisible, and everywhere, exactly matching the properties of the mysterious stuff holding galaxies together. Second, the Higgs boson's mass. On its own, the Higgs should be impossibly heavy due to quantum fluctuations, yet it's curiously light. Sussy superpartners would cancel out those fluctuations like cosmic counterweights, preserving the delicate balance that makes our universe possible. But the real kicker, supersymmetry, isn't just about new particles, it's about symmetry on a staggering scale. It suggests space-time has hidden dimensions where particles spin differently, like dancers performing a routine we can't see. Unlocking this could reveal why the universe favors matter over antimatter, or why gravity is billions of times weaker than other forces. It's as if we've been studying a painting under dim light, and Sussy is the switch that reveals the full spectrum of colors hidden in the brushstrokes. The next few years will be decisive. Upgraded colliders and ultra-sensitive dark matter detectors are poised to hunt these superpartners with unprecedented precision. If they're found, it won't just validate a theory, it'll open a portal to a shadow universe teeming with particles we've never imagined, rewriting the rules of reality as we know them. And if not, even failure would be a revelation, forcing us to confront the unnerving possibility that nature's deepest symmetries are stranger than anything we've dared to dream. The cosmic web stretches across the observable universe like a colossal neural network, filaments of galaxies weaving through voids, connecting in nodes so vast they make superclusters look like mere specks. For decades, astronomers assumed this structure emerged from chaos, a natural outcome of gravity clumping matter over billions of years. But recent supercomputer simulations have revealed something extraordinary. This web isn't just a tangled mess. It's a masterpiece of precision, its threads aligning with mathematical symmetries so exact, they hint at a hidden architectural blueprint for the cosmos itself. Take the Fibonacci sequence, that famous spiral of numbers found in sunflower seeds and nautilus shells. When researchers mapped the angles between cosmic filaments, they discovered these same ratios recurring at scales spanning hundreds of millions of light years. It's as if the universe took a mathematical rule born on Earth and scaled it up to galactic proportions. Even more startling, the distribution of voids. Those empty bubbles between filaments follows patterns eerily similar to soap foam's geometry, where surfaces minimize energy by obeying strict geometric rules. Nature, it seems, has a favorite playbook, and it's written in equations that transcend size. Here's where it gets mind-bending. These symmetries aren't just aesthetic, they might hold the key to dark matter's influence. Simulations that incorporate dark matter's gravitational pull produce cosmic webs strikingly close to the real thing, but only when certain symmetries are preserved. Remove those underlying rules, and the virtual universe collapses into clumps or scatters into disorder. This suggests dark matter isn't just an invisible scaffold, it's an active participant in maintaining cosmic order, like an unseen conductor guiding an orchestra of galaxies. But the real revelation lies in what this means for the early universe. The cosmic web's symmetry couldn't have emerged late in cosmic history. Its seeds were planted in the first sliver of a second after the Big Bang, when quantum fluctuations' tiny ripples in space-time stretched into vast patterns during inflation. Those primordial wrinkles became the template for everything that followed, meaning the universe's largest structures might owe their existence to quantum physics operating at scales 1 trillion times smaller than an atom. It's like discovering the DNA of the cosmos, with strands so long they wrap around reality itself. What does this teach us? First, randomness might be an illusion. What looks chaotic could be the surface ripple of deeper, more elegant laws. Second, the universe seems obsessed with efficiency. Just as bees build honeycombs with minimal wax, the cosmic web arranges matter to maximize gravitational stability while minimizing wasted space. And third, we're not just observers of this order, we're embedded in it. Every atom in your body was forged in stars that trace back to those ancient filaments, making you part of the symmetry you're now struggling to comprehend. The cosmic web isn't just a map of where galaxies live. It's a fingerprint left by the universe's hidden architects, a clue that chaos and order might be two sides of the same cosmic coin. And as we decode more of its patterns, we're not just charting space, we're reading the universe's autobiography, written in geometry across the sky. Neutrinos are the universe's ultimate escape artists, particles so slippery, they pass through entire planets like ghosts through walls. Every second, trillions of them stream through your body without a trace, as if the laws of physics barely apply to them. For decades, this elusiveness made neutrinos a frustrating mystery. But now, scientists are uncovering something astonishing. These ghostly particles might be breaking the rules not out of chaos, but because they're obeying a hidden symmetry deeper than anything we've imagined. Take the case of neutrino oscillations, a phenomenon so bizarre it upended particle physics. When neutrinos travel through space, they don't stay the same. They shapeshift between three flavors: electron, muon, and tau, like a chameleon cycling through colors mid-stride. At first, this seemed like random quantum noise, but the math tells a different story. These oscillations follow precise patterns, almost as if the neutrinos are dancing to a rhythm written in a dimension we can't see. The key, a potential symmetry called mu-tau reflection, where the probabilities of muon and tau neutrinos transforming into each other are mirror images. It's as if nature built a secret backdoor into these particles, a geometric rule that balances their behavior with near-perfect precision, but the plot thickens. Recent experiments like IceCube and Supersymmetry have spotted neutrinos doing something even stranger, arriving at detectors with energies that defy standard predictions. Some theorists argue this could hint at a new symmetry principle, one that governs not just neutrinos but all particles. Imagine a cosmic seesaw, where the lightness of neutrinos is counterbalanced by the heaviness of yet undiscovered particles. This seesaw mechanism isn't just elegant math, it could explain why neutrinos have mass at all, a question that's puzzled physicists since their discovery. Here's where it gets revolutionary. If this symmetry holds, it might connect neutrinos to dark matter. The same hidden physics that makes neutrinos nearly massless could also create a stable, invisible particle that fills the cosmos, the very stuff we call dark matter. Picture a shadow world where every neutrino we detect has a heavier, slower-moving counterpart, lurking just beyond our instruments. These sterile neutrinos could be the missing link between the particle zoo we know and the dark sector we're desperate to map. The implications are staggering. Neutrinos might be messengers from a hidden layer of reality, whispering clues about symmetries that unify all forces. If we decode their language, we could crack open the Standard Model's biggest puzzles: why matter dominates antimatter, why gravity is so weak, even why the universe exists at all. Upcoming experiments like Dune and Hyper-Kamiok are tuning their detectors to listen. The question isn't just whether neutrinos hold secrets, it's whether we're ready to hear what they've been trying to tell us all along. What if every universe in the multiverse isn't a random roll of the cosmic dice, but a deliberate variation on the same symmetrical theme? Imagine a grand piano with infinite keys, each playing a slightly different version of the same fundamental melody, except in this case, the keys are entire universes, and the melody is the underlying symmetry that shapes their very laws. This isn't just speculation. String theory, the framework that paints reality as tiny vibrating strings, suggests that the multiverse could be a vast symphony of symmetrical branches, each one a unique but related expression of the same mathematical harmony. Think of it like a kaleidoscope. With every twist, the same colored fragments rearrange into new patterns, yet they're always bound by the mirror-like symmetry of the device itself. In the multiverse, the twists might be different ways symmetry breaks during the birth of each universe. One universe could have slightly weaker gravity, another might host stronger nuclear forces, but all of them stem from the same symmetrical template, like siblings with different talents but shared DNA. Even the quirks we can't explain in our own cosmos, like the inexplicably small mass of the Higgs boson or the unnerving fine-tuning of dark energy, might just be local glitches in a grander pattern. Here's where it gets wild. Some theories propose that these symmetrical branches aren't just hypothetical. They could leave tangible traces. If another universe bumped against ours in the early cosmos, the collision might have imprinted odd patterns in the cosmic microwave background, like a fingerprint on the sky. Scientists are already scouring this ancient light for asymmetrical anomalies that could hint at a neighbor universe nudging ours long ago, even more mind-bending. The multiverse's symmetries might explain why our universe seems oddly hospitable to life. If countless variations exist, then of course we'd find ourselves in one where the symmetries bent just right to allow stars, planets, and conscious observers. But the real revelation isn't just that the multiverse exists, it's that symmetry might be the glue holding it all together. Like a master artist working in infinite dimensions, nature could be painting with the same palette of mathematical relationships across every reality, tweaking the brushstrokes but never the colors. Whether that's beautiful or unsettling depends on how you look at it. Either way, it suggests that even in a sea of infinite possibilities, nothing is truly random. Every universe, including ours, could be a single note in a chord so vast, we're only now beginning to hear its echo. Dark energy is the universe's greatest magic trick, an invisible force pushing galaxies apart faster and faster, as if space itself has a hidden accelerator pedal. For years, scientists assumed this expansion would slow down after the Big Bang's initial burst, like a car coasting after running out of gas. Instead, the cosmos is flooring it, and no one knows why. But what if the answer isn't some mysterious energy field? What if dark energy is just a symptom of something far deeper, a symmetry so fundamental it's been hiding in plain sight within Einstein's own equations? Einstein initially included a term in his theory of general relativity called the cosmological constant, a mathematical placeholder representing a repulsive force that could balance gravity. He later dismissed it as his greatest blunder, but modern observations suggest he might have been right for the wrong reason. The cosmological constant could actually be a signature of vacuum symmetry, a property of empty space itself. Think of the vacuum not as true emptiness, but as a seething quantum foam where particles flicker in and out of existence. These fleeting fluctuations generate energy, and if they obey a hidden symmetry, their collective push might explain cosmic acceleration without invoking any exotic dark energy at all. Here's where it gets radical. Some theorists argue this symmetry isn't just mathematical elegance, it's a necessary feature of reality. Just as a spinning top stays upright due to rotational symmetry, the universe's expansion might be governed by a similar balance. Modified gravity theories, like those involving mirror symmetries in higher dimensions, suggest that what we call dark energy could be gravity leaking into our universe from a parallel one, or the echo of a symmetry broken during the Big Bang. Imagine two sheets of paper pressed together. When one warps, the other bends in response. If space-time has a hidden partner, their interplay might mimic the effects of dark energy without any new physics. The evidence is tantalizing. When astronomers map the universe's large-scale structure, they find voids and clusters distributed in patterns that align eerily well with certain symmetric models. Even more compelling, the rate of cosmic acceleration appears suspiciously fine-tuned, as if it's precisely the value needed to maintain a deeper equilibrium. It's like discovering that a chaotic symphony is actually following sheet music we couldn't see, but the real mind bender. If this symmetry exists, it could mean dark energy isn't a thing at all, but a shadow, a side effect of space-time's true geometry. That would turn cosmology on its head, replacing the hunt for exotic particles with a quest to decode the universe's hidden harmonies. Future telescopes like Euclid and the Vera Rubin Observatory are already searching for clues in the distortion of ancient light. What they find might not just solve the dark energy puzzle. It could reveal that the cosmos isn't expanding randomly, but unfolding according to a symmetry as old as time itself. Einstein's general relativity paints gravity as the elegant curvature of space-time, a cosmic dance where planets and stars glide along invisible grooves. Meanwhile, quantum mechanics describes a subatomic world buzzing with uncertainty, where particles pop in and out of existence like fireflies in a storm. These two theories work flawlessly in their own domains, but bring them together, and the math explodes into nonsense. Gravity refuses to play by quantum rules, and particles ignore relativity's smooth geometry. It's as if the universe wrote two instruction manuals for itself in languages that can't be translated. Yet hidden in this chaos, physicists are spotting a glimmer of hope, a shared dialect spoken by both worlds, and it's all about symmetry. At the heart of this puzzle lies a concept called gauge symmetry, a kind of mathematical harmony that governs how forces interact. Think of it like a game of cosmic telephone, where particles pass messages to one another using fields that must stay perfectly balanced. Electromagnetism and the nuclear forces already obey these gauge symmetries, which is why quantum theory describes them so well. Gravity, though, has always been the rebel until now. Fresh theories suggest that gravity, too, might be a gauge force at its core, just one that's been hiding in geometric disguise. Picture a sculptor working with two blocks of marble, one carved into a detailed statue, the other left rough and unshaped. They're the same material, but only one reveals its true form. If gravity's gauge symmetry has been buried beneath the complexity of space-time's curves, uncovering it could bridge the quantum relativity divide. Clues are already emerging from unexpected places. When LIGO detected gravitational waves, ripples in space-time from colliding black holes, it didn't just confirm Einstein's predictions. It revealed fingerprints of quantum effects woven into those waves, subtle tremors that hint at gravity's deeper structure. Some researchers argue these tremors align with predictions from loop quantum gravity, a framework where space-time isn't smooth but made of tiny, discrete loops vibrating in perfect gauge symmetric harmony. It's like listening to a symphony and suddenly hearing the faint hum of a tuning fork, proof that the orchestra tunes itself to a hidden pitch. But the real breakthrough might lie in the holographic principle, which suggests that gravity's gauge symmetry could emerge from quantum information dancing on the boundary of the universe. Imagine a 3D movie projected from a 2D screen. The depth, the motion, all feel real, but they're just shadows of data encoded flat. Similarly, gravity's force might be a projection of quantum interactions happening on a distant, lower dimensional surface. If true, this would mean Einstein's curvature is an illusion, a collective effect of trillions of quantum bits maintaining perfect gauge symmetry across the cosmic horizon. The implications are staggering. Uniting gravity and quantum mechanics wouldn't just fill a textbook gap. It could rewrite our understanding of black holes, the Big Bang, even the nature of reality itself. Are singularities knots of tangled gauge fields? Was the early universe a symmetry-breaking explosion that birthed time itself? Experiments like LIGO and future quantum gravity probes are inching us closer to answers. But one thing's certain, the solution won't come from forcing gravity into quantum clothes or vice versa. It'll emerge from the symmetry they've shared all along, a secret handshake waiting to be decoded. And when we crack it, the universe might finally whisper its grandest secret, that every force, from the mightiest to the most fragile, sings the same fundamental note. The ancient Greeks called it the music of the spheres, the idea that planets and stars moved in perfect harmonic ratios, their celestial dance producing a symphony too vast for human ears to hear. For millennia, this was dismissed as poetic fantasy, but today, astronomers are discovering that the cosmos really does sing, and its song might hold the key to unlocking symmetries we never thought possible. Take our own sun, for example. Beneath its fiery surface, pressure waves ripple outward like sound waves in a colossal bell, causing the entire star to vibrate at precise frequencies. These stellar oscillations aren't random noise, they follow mathematical patterns so exact, scientists can use them to measure the sun's internal structure, almost like doing a cosmic ultrasound. But here's where it gets wild. When researchers analyzed these solar vibrations alongside those of distant stars, they noticed something eerie. The frequencies often align with the same harmonic ratios found in musical scales, as if the universe has a preferred key signature. A middle C hummed by a star 1,000 light-years away might resonate at double the frequency of one in our own solar system, creating an octave relationship across unimaginable distances. Black holes take this cosmic concert even further. When two of these gravitational monsters collide, they don't just send out gravitational waves, they ring like mallets striking a drum, producing quasi-normal modes that decay in predictable mathematical sequences. The pitch and decay rate of these tones depend entirely on the black hole's mass and spin, meaning every singularity has its own unique acoustic fingerprint. Some theorists now suspect these tones might encode hidden symmetries related to quantum gravity, vibrations so precise they could reveal how space-time behaves at the smallest scales. Imagine tapping a wine glass to determine not just its shape, but the molecular structure of the glass itself. That's the level of detail we're talking about. But the most astonishing melodies come from the cosmic microwave background, the afterglow of the Big Bang. When scientists converted its temperature fluctuations into sound waves, they heard a deep, resonant hum, a bass note reverberating from the dawn of time. This isn't just a novelty, it's a direct snapshot of the universe's infancy, a fossilized sound wave frozen in expansion. The harmonics of this primordial tone match predictions from inflationary theory so closely, they've become one of our strongest pieces of evidence for the Big Bang. It's as if the universe left us a voicemail from its first moments, and we're only now learning how to play it back. What does this all mean? If celestial harmonies follow mathematical symmetries, then music isn't just an earthly art, it's woven into the fabric of reality. The same ratios that make a Beethoven symphony stirring might govern the spin of galaxies or the pulse of quasars. Some researchers even speculate that these vibrations could be a universal language, a way for advanced civilizations to communicate across the void by tuning into the cosmos's natural frequencies. Whether that's true or not, one thing is clear: the universe isn't silent. It's a grand, vibrating instrument, and every star, every black hole, every atom is part of the ensemble. The question isn't whether the cosmos sings, it's whether we're listening closely enough to decipher the tune. Magnets are familiar. Every child knows they have two poles, a north and a south, inseparable like two sides of a coin. Break a magnet in half and you don't isolate a single pole. You get two smaller magnets, each with its own pair of poles. But what if nature isn't so rigid? What if, hidden in the chaos of the early universe, particles with only one magnetic pole, monopoles, were forged in the fire of creation, waiting to be found? This isn't science fiction. The existence of magnetic monopoles was predicted over a century ago by physicist Paul Dirac, who showed that their presence would elegantly explain why electric charge comes in discrete, quantized units. It's as if the universe left a clue in the math, whispering that symmetry demands their existence. Yet despite decades of searching, from deep underground labs to cosmic ray detectors, monopoles have remained frustratingly elusive. Some scientists began to wonder if they were chasing a ghost, but here's the twist: monopoles might not be missing. They could just be hiding in plain sight, frozen relics of a time when the universe was 1 trillion degrees hotter. Picture the early cosmos as a bubbling cauldron of energy where symmetries ruled unchallenged. As the universe expanded and cooled, those symmetries shattered like glass, and in the cracks, magnetic monopoles may have formed like cosmic knots. If they exist, they'd be staggeringly heavy, millions of times the mass of a proton, and incredibly rare, drifting through space like solitary icebergs in an ocean of dark matter. The hunt has taken a thrilling turn thanks to new theories suggesting monopoles could be masquerading as something else entirely. Some models propose that these elusive particles might cluster in the cores of neutron stars, their immense gravity trapping and compressing them into exotic states. Others speculate that monopoles could be hiding within cosmic strings, defects in space-time left over from the Big Bang, like pearls threaded on an invisible necklace. Even more radical is the idea that monopoles aren't particles at all, but temporary distortions in the quantum vacuum, flickering in and out of existence too briefly for our detectors to catch. Why does this matter? Because finding a magnetic monopole wouldn't just check a box on a theorist's wish list, it would rewrite the rules of electromagnetism. Monopoles could be the missing link unifying electricity and magnetism into a single, symmetrical force, much like how the discovery of the Higgs boson completed the Standard Model. They might even hold clues to dark matter, inflation, or the universe's matter-antimatter imbalance. Imagine stumbling upon a key that unlocks not just one door, but an entire hallway of cosmic mysteries. The search is far from over. Next-generation experiments like the Mo-Edel detector at CERN are scanning particle collisions for monopole signatures, while astronomers scour neutron stars for anomalies that might betray their presence. Whether these solitary poles are lurking in the depths of space or buried in the quantum foam, one thing is certain: if they're found, the symmetry of the universe will finally feel complete. And if not, their absence would be just as profound, forcing us to rethink whether nature's deepest symmetries are more subtle or more strange than we ever imagined. We've spent centuries mapping the forces that rule our universe: gravity's relentless pull, electromagnetism's crackling energy, the nuclear forces binding atoms together. But what if the cosmic rulebook has a missing chapter? Enter the fifth force hypothesis, a radical idea gaining traction as physicists stumble upon particles behaving in ways that defy the known laws. Picture a game of billiards where one ball suddenly veers off course without explanation, as if nudged by an invisible hand. That's the enigma researchers face when certain subatomic particles decay slightly too fast or scatter at unexpected angles, anomalies that can't be chalked up to measurement errors. These aren't glitches, they might be glimpses of a hidden force, one governed by symmetries so subtle, we've only just begun to sense their presence. The clues lie in the delicate dance of muons, heavier cousins of electrons that wobble like spinning tops when placed in magnetic fields. According to the standard model, this wobble should follow precise rhythms, yet recent experiments at Fermilab and CERN reveal a tantalizing mismatch. The muon's dance is offbeat, as if an unseen partner is tugging at them mid-spin. Theorists argue this could signal a fifth force mediated by an undiscovered particle, perhaps a Z-prime, boson, or a leptoquark, carrying an interaction that doesn't fit the four-force framework. Imagine discovering a new color in the spectrum, one that's been filtering reality all along without us realizing it. But here's where symmetry takes center stage. Every known force arises from a specific type of gauge symmetry mathematical harmonies that dictate how particles interact. If a fifth force exists, it too would emerge from a symmetry, possibly one that's been broken since the universe's infancy, leaving only faint traces in high-energy collisions. Some models suggest this force could act as a cosmic bridge, linking ordinary matter to dark matter through shared symmetrical rules. Think of it like a secret handshake between two clandestine societies. We can't see the dark matter members, but their influence ripples through the motions of particles we can observe. The implications are staggering. A fifth force might explain why dark matter, which outweighs visible matter 5-to-1, barely interacts with ordinary stuff except through gravity. It could also solve the proton radius puzzle, where measurements of the proton size disagree depending on the experimental method, as if an unknown force subtly alters the results. Even more tantalizing, this force might be tied to supersymmetry, the theoretical framework predicting every particle has a heavier twin. If confirmed, it wouldn't just expand the periodic table of physics, it would redefine the very fabric of cosmic interactions. Skeptics argue these anomalies could still be statistical flukes or unaccounted for errors, but the hunt is intensifying. Upgraded particle colliders and ultra-precise quantum sensors are scanning for deviations with unprecedented sensitivity. Whether the fifth force is real or not, its possibility reminds us that the universe's symmetries might be richer, stranger, and more layered than we ever imagined. And if we find it, the discovery won't just add a page to the physics textbook. It could tear out the table of contents and rewrite it from scratch. The human brain is often called the most complex object in the known universe, a 3-pound universe of firing neurons, electrical impulses, and mysteries we've barely begun to unravel. But what if consciousness, that shimmering sense of self and awareness, isn't just a byproduct of biology? What if it's the universe itself recognizing its own symmetry through the lens of our minds? This isn't New Age mysticism, it's a radical hypothesis gaining traction at the edges of neuroscience and quantum physics, where researchers are probing whether the patterns of our thoughts might emerge from the same fundamental symmetries that shape black holes and subatomic particles. Take microtubules, the tiny protein structures inside neurons that some scientists believe could be quantum computing elements. Their lattice-like arrangements vibrate at frequencies that eerily mirror mathematical symmetries found in quantum field theory, almost as if the brain is tuned to the universe's hidden harmonies. Nobel laureate Roger Penrose and anesthesiologist Stuart Hameroff argue that these vibrations might orchestrate consciousness through quantum coherence, a delicate state where particles synchronize across microscopic distances, creating a unified field of perception. It's like imagining your morning coffee not just as a drink, but as trillions of water molecules dancing in perfect symmetry, their collective motion giving rise to heat, steam, and taste. The controversy here is palpable. Mainstream neuroscience dismisses quantum consciousness as speculative, pointing out that the warm, wet environment of the brain should destroy fragile quantum states almost instantly. But proponents counter with a startling observation. General anesthesia works by disrupting these very microtubule vibrations, selectively switching off awareness while leaving non-conscious brain functions intact. If consciousness were purely classical, why would subtle quantum interference play such a pivotal role in its on-off switch? The symmetry connection grows even stranger when you consider near-death experiences, where patients report vivid, structured visions even when their brains show no measurable activity. Could these be glimpses of a deeper, symmetry-driven layer of reality flickering into view? Here's where the theory takes a cosmic turn. If consciousness stems from quantum symmetries, then the universe might not just contain observers, it might be observing itself through us. Think of a mirror reflecting a mirror, creating an infinite hall of self-referential images. In this view, your thoughts aren't just neural chatter, they're localized expressions of universal patterns, like eddies in a river that momentarily take shape before dissolving back into the flow. This idea, dubbed panpsychism, suggests that even elementary particles might possess a whisper of proto-consciousness, with human awareness being a symphonic convergence of these tiny voices. Skeptics rightly demand evidence, and it's coming from unexpected places. Experiments with psychedelics show that substances like psilocybin dramatically increase the brain's entropy, a measure of chaotic activity, yet users report feelings of profound unity and connection. This paradox aligns with symmetry principles, where higher entropy states often reveal hidden patterns, like how shaking a kaleidoscope creates more intricate designs. Meanwhile, advanced AI systems, despite their computational power, show no signs of self-awareness, hinting that consciousness might require something beyond mere information processing, perhaps a quantum symmetric substrate we haven't yet engineered. The implications are staggering. If consciousness is rooted in cosmic symmetry, then free will might not be an illusion but an expression of deeper deterministic harmonies. Mental disorders could arise from symmetry breaks in neural quantum states, opening doors to revolutionary treatments. Even our search for extraterrestrial intelligence might need recalibration. Instead of looking for radio signals, we might listen for coherent quantum vibrations echoing through the cosmos. Whether this theory holds or crumbles under scrutiny, one thing is certain: the mere possibility forces us to rethink the boundary between mind and universe. If true, every moment of insight, every flash of creativity, every surge of emotion isn't just happening inside your skull. It's the cosmos thinking itself into existence, one symmetrical thought at a time. And that might be the most humbling revelation of all. For nearly a century, physicists have chased what Einstein called his Holy Grail, a single, elegant framework that could explain all the forces of nature, from the whirl of galaxies to the buzz of quantum particles. The dream seemed to fade as the decades passed, with the standard model stubbornly resisting unification with gravity. But now, in an astonishing twist, the old quest is roaring back to life, fueled by symmetries so powerful they might finally stitch together reality's fractured rulebook. At the heart of this revival lies a startling realization. The forces we once thought irreconcilable might be different faces of the same cosmic symmetry, frozen into fragments during the universe's fiery birth. Picture a prism splitting sunlight into a rainbow. What if electromagnetism, gravity, and the nuclear forces are just spectral shards of a primordial superforce? Recent experiments at particle colliders have spotted eerie unifications at ultra-high energies, where electromagnetic and weak nuclear forces merge into a single, electroweak interaction, as predicted by Nobel-winning work in the 1970s. But the real shock came when theorists noticed deeper patterns lurking in the datum, mathematical harmonies suggesting even gravity, might join the party under extreme conditions, like temperatures 1,000,000,000,000 times hotter than the sun. The key lies in a class of symmetries called Lie groups, intricate geometric relationships that govern how particles interact. These aren't just abstract doodles, they're the universe's hidden wiring. For example, the symmetry group dubbed E8, a mesmerizing 8-dimensional shape with 248 symmetries, might encode all known particles and forces as vibrations in its complex geometry. Imagine plucking a guitar string and hearing not just a note, but the entire symphony of creation resonating from a single pluck. That's the promise of these unified symmetries, a cosmic chord so profound, it could reveal why an electron's charge balances a proton so precisely, or why the vacuum of space hums with just the right energy to allow galaxies and life to exist. Skeptics argue that unification energies are so unimaginably high, far beyond what any collider could reach, that the theory might forever remain untestable. But nature has handed us a workaround: cosmic relics. Just as archaeologists reconstruct ancient civilizations from pottery shards, physicists are scouring the universe for remnants of the unification epoch. Neutrinos, those ghostly particles that barely interact with matter, might carry imprints of symmetries broken moments after the Big Bang. Even the humble proton's stability could be a clue. If it decays in certain ways, as some unified theories predict, it would betray the fingerprints of a grander symmetry at work. The implications stretch beyond equations. If unification is real, it would mean that every flicker of lightning, every orbit of a planet, every bond holding atoms together is governed by the same elegant principle, a symmetry so vast. It makes the cosmos feel less like a chaotic accident and more like a masterpiece composed in a single, breathless act of creation. And the most thrilling part, we might be on the verge of hearing its opening note. A butterfly flapping its wings might cause a hurricane halfway across the world, but that's nothing compared to what quantum particles can do. At the smallest scales imaginable, empty space is anything but empty. It's a seething ocean of virtual particles popping in and out of existence, their fleeting lives governed by the bizarre rules of quantum mechanics. For decades, scientists dismissed these fluctuations as background noise, too small and random to matter on cosmic scales. But here's the revelation: these quantum tremors might be the universe's most meticulous architects, sculpting everything from galaxy clusters to the very conditions that make life possible, all by obeying hidden symmetrical laws we're only beginning to decipher. Consider the cosmic microwave background, the afterglow of the Big Bang. When scientists mapped its faint temperature variations, they expected randomness. Instead, they found patterns: delicate, symmetrical ripples that matched predictions of quantum fluctuations stretched to galactic proportions during inflation. It's as if the universe took a whisper from the quantum realm and amplified it into a shout that echoes across billions of light years. These ripples became the seeds for all structure in the cosmos, meaning every star, every planet, even you, exist because of quantum symmetry playing out on a stage almost infinitely larger than itself. The real magic lies in the numbers. The strength of these fluctuations is absurdly fine-tuned. If they'd been slightly stronger, matter would have clumped into monstrous black holes long before stars could form. Slightly weaker, and galaxies might never have coalesced at all. This Goldilocks precision, neither too hot nor too cold, has baffled physicists for generations. But new research suggests an elegant answer. The fluctuations aren't random. They're constrained by symmetries so deep they act like cosmic guardrails, ensuring the universe stays on a path that allows complexity to emerge. One such symmetry is conformal invariance, a property that lets quantum systems scale infinitely without changing their essential rules. Imagine a snowflake that looks identical whether you view it under a microscope or from space. This symmetry might explain why quantum fluctuations imprint so perfectly onto the large-scale universe, because the laws governing them don't care about size. Another clue comes from supersymmetry, which posits that every particle has a twin with mirrored properties. Though we haven't found these twins yet, their existence could balance the quantum chaos, fine-tuning fluctuations to levels that permit galaxies and life. But the most mind-bending idea, these symmetries might not just explain our universe's structure, they could reveal it's part of a multiverse. In this view, countless universes bubble into existence, each with different fluctuation strengths. Most are sterile, but a rare few, like ours, hit the symmetry jackpot, creating the perfect conditions for atoms, chemistry, and eventually, minds capable of marveling at their own existence. It's like a cosmic lottery where the winning ticket is written in the language of quantum geometry. The implications are profound. If true, it means the quantum butterfly effect isn't just about chaos, it's about order emerging from the smallest symmetries. Every time you take a breath or gaze at the stars, you're witnessing the aftermath of quantum rules playing out with near mathematical perfection, and the most humbling thought. The same symmetries that sculpted galaxies might also pulse through the neurons in your brain, linking the vast and the infinitesimal in a dance older than time itself. The universe has a dirty little secret: it's playing favorites. According to every known law of physics, matter and antimatter should have been created in equal amounts during the Big Bang, locked in a perfect symmetrical dance of mutual annihilation. Yet here we are, in a cosmos overflowing with galaxies, stars, and planets made entirely of matter, with barely a trace of its opposite. It's like flipping a coin trillions of times and getting heads every single time, a statistical impossibility screaming that something's broken in the cosmic rulebook. Enter CERN Alpha experiment, where scientists are trapping anti-hydrogen atoms, the simplest form of antimatter, in magnetic cages to study their behavior with atom-splitting precision. What they've found is electrifying. When anti-hydrogen spectral lines were measured, they matched regular hydrogens almost perfectly, but not quite. That almost is the crack in the universe's facade. If matter and antimatter were perfect mirror images, those lines should overlap exactly. The fact that they don't hints at a fundamental asymmetry, a cosmic tilt that might explain why matter won the ultimate lottery. This imbalance isn't just a quirk. It's written into the fabric of reality through something called charge parity violation. Normally, the laws of physics treat particles and their anti-particle counterparts equally, whether you're observing them directly or through a mirror. But certain exotic particles like kaons and B mesons break this rule. When they decay, they do so slightly more often into matter than antimatter, as if the universe has a hidden bias. Picture a pair of identical twins raised the same way, yet one consistently grows taller. That's the level of cosmic unfairness we're dealing with. The stakes couldn't be higher. Without this asymmetry, every particle of matter would have met its antimatter twin in a flash of gamma rays, leaving behind a sterile void. The fact that you exist to watch this video means the scales tipped by just 1 part in a billion in favor of matter. The question is, why? Some theorists argue it's tied to the Higgs field, the same energy web that gives particles mass. Others suspect undiscovered particles, like heavy neutrinos, tipped the balance during the universe's first microseconds. But the most radical idea, this isn't a flaw, it's a feature. The same asymmetry that saved the cosmos from self-destruction might also be the reason complex structures, from DNA to galaxy clusters, could emerge. Symmetry is beautiful, but perfection is brittle. A universe in perfect balance would have cancelled itself out. Instead, we got a cosmos with just enough lopsidedness to spawn black holes, butterflies, and beings capable of wondering why they're here at all. CERN next-generation colliders aim to recreate these primordial imbalances with even greater precision, hunting for the exact moment symmetry broke. Whatever they find, one thing's certain: the universe isn't just asymmetrical by accident, it's asymmetrical by design, and that tiny, ancient bias might be the reason anything exists at all. Black holes have long been the ultimate cosmic enigmas, regions where gravity is so intense, not even light can escape. But what happens to the information that falls in? For decades, physicists assumed it was irretrievably lost, scrambled into quantum noise beyond recognition. Then came the firewall paradox, a mind-bending idea suggesting that the event horizon, the point of no return, might not be the serene boundary we imagined. Instead, it could be a raging inferno of high-energy particles, a literal wall of fire waiting to incinerate anything daring enough to cross. This radical proposal emerged from a clash between quantum mechanics and general relativity, two pillars of physics that refuse to play nice when black holes are involved. But here's the twist: firewalls might not exist at all, at least not if the universe has its way. A groundbreaking symmetry-based model is turning this fiery nightmare on its head, proposing that the event horizon isn't a destructive barrier but a delicate holographic screen, preserving information in ways we're only beginning to understand. Picture a waterfall where the water at the edge doesn't plunge into chaos, but instead freezes into an intricate ice sculpture, encoding every ripple and droplet in perfect crystalline detail. That's the essence of this new theory. Black holes might not annihilate information but transform it, imprinting it onto their surfaces like cosmic archivists. The key lies in a symmetry called quantum error correction, a concept borrowed from cutting-edge computing. Just as error-correcting codes protect data in a noisy environment, black holes could use similar principles to safeguard information from total destruction. Imagine a message written on a piece of paper, then shredded. Normally, it's gone forever. But if the shreds are cut in a specific symmetrical pattern, they can be reassembled perfectly. No missing pieces, no lost meaning. Black holes might operate the same way, using quantum entanglement to weave infalling data into a holographic tapestry on their event horizons. This isn't just theoretical sleight of hand. The math reveals that firewalls would violate a fundamental symmetry known as local Lorentz invariance, which ensures that the laws of physics remain consistent for all observers, regardless of their motion. A firewall would create a preferential frame of reference, a cosmic hotspot that breaks the universe's democratic rules. Nature abhors such asymmetry, which is why the firewall paradox has sparked such fierce debate. If black holes really did burn up information, it would mean the universe has a glaring inconsistency, a crack in the foundation of reality itself. Yet the implications stretch even further. If information isn't lost but preserved, it could mean black holes are the ultimate quantum computers, performing calculations on scales we can't yet fathom. Their event horizons might be buzzing with encoded data, a library of cosmic history written in the language of entanglement. And when black holes eventually evaporate via Hawking radiation, that information could be gently released back into the universe, like a message in a bottle washing ashore after eons adrift. The most thrilling part: we might not have to wait centuries to test this. Advanced gravitational wave detectors could soon pick up subtle echoes from merging black holes' ripples in space-time that carry fingerprints of their event horizon structure. If those echoes match the predictions of symmetry-preserving models, it would be like catching a black hole red-handed, quietly safeguarding secrets instead of burning them to ashes. So forget the firewall. The real story isn't about destruction, it's about transformation. Black holes might not be the universe's shredders, but its most meticulous scribes, etching the story of everything that falls into them onto the fabric of space-time itself. And if that's true, then the most terrifying objects in the cosmos could also be the most eloquent storytellers, whispering the universe's secrets in a language of perfect symmetry. Space and time feel as fundamental as existence itself, the stage upon which the universe plays out its grand drama. But what if the stage is an illusion? What if space and time aren't the bedrock of reality, but something far stranger, emergent properties, like the wetness of water or the melody of a song, arising from a hidden symphony of quantum connections? This isn't just a thought experiment. A growing chorus of physicists now suspects that the dimensions we move through daily might be shadows cast by something deeper, a reality where the concepts of here and now dissolve into a web of pure symmetry. The clues come from quantum entanglement, that spooky link binding particles across vast distances. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. This defies our intuition about space. How can information seem to leap across the cosmos without crossing the distance in between? The answer might be that space itself isn't primary, but stitched together by these quantum threads, like a 3D mirage projected from a network of invisible connections. Picture a movie screen. What looks like a seamless image is actually countless pixels glowing in precise coordination. Similarly, space-time could be the collective glow of entangled quantum bits, with every star, every planet, every atom just a node in this cosmic neural network. This idea, called emergent space-time theory, turns physics inside out. Instead of particles existing within space, space emerges from the relationships between particles. Think of it like a crowd at a concert. The space between people isn't a fixed backdrop, but created by their interactions, shifting as they move. In the quantum realm, these interactions are governed by entanglement, and the geometry of space-time might simply be a way to describe their intricate dance. Some models even suggest that black holes, where space and time warp beyond recognition, are places where this underlying quantum fabric becomes visible, like seeing the pixels when you press your face too close to the screen. The math behind this is as beautiful as it is bizarre. In certain quantum gravity theories, space-time's smooth curvature arises from the entanglement entropy between particles, a measure of how much information they share. More entanglement means tighter connections, which our brains interpret as closeness in space. This could explain why the universe appears continuous despite being built from discrete quantum parts, much like a digital photo looks smooth until you zoom in far enough to see the pixels. Even gravity, which Einstein described as the bending of space-time, might be an emergent effect, a statistical tendency of quantum bits to organize themselves in ways that mimic curvature. But the most startling implication, time itself might not be fundamental. In some versions of emergent space-time, what we perceive as the flow of time could be a side effect of quantum systems evolving toward higher entropy, like a deck of cards shuffling itself into disorder. The past and future would then be illusions, artifacts of our limited perspective as creatures stuck in the cosmic computation. It's as if the universe is a cosmic film strip, and we're mistaking the progression of frames for real movement, unaware that every moment exists simultaneously in a higher dimensional whole. Experiments are already probing these radical ideas. Quantum simulators, devices that mimic quantum systems, have shown hints of space-time emergence in controlled settings. When researchers entangled qubits in specific patterns, they found the system's geometry began to behave like a tiny, synthetic universe, complete with its own emergent space. Meanwhile, astrophysicists are scouring the cosmic microwave background for anomalies that might betray the quantum roots of space-time, like cracks in a painted facade. If emergent space-time theory holds, it won't just rewrite textbooks, it'll redefine what reality means. The solid ground beneath your feet, the vast expanse of the night sky, even the ticking of the clock on your wall, all might be secondary phenomena, surface ripples on a quantum ocean whose depths we've only begun to fathom. And the most humbling thought, the universe isn't happening in space and time. Space and time are happening in the universe, a fleeting pattern in something far richer, stranger, and more symmetrical than we ever dreamed. Imagine the universe in its first trillionth of a second, a seething, superheated speck smaller than a proton. Then, in a blink, it exploded outward faster than light itself, stretching from quantum scales to cosmic vastness in less time than it takes light to cross an atom. This is cosmic inflation, the theory that's dominated cosmology for decades. But what if we've had it backward? What if inflation wasn't just a random expansion, but the universe snapping into a new symmetrical order, like molten iron aligning into perfect crystals as it cools? The idea hinges on symmetry breaking, a phenomenon as simple as it is profound. Picture a pencil balanced perfectly on its tip. For a fleeting moment, it's symmetrical, poised in flawless equilibrium. But the slightest disturbance sends it toppling, choosing one direction over all others. The early universe might have undergone a similar transition. As it cooled, a primordial symmetry, perhaps one unifying all fundamental forces, shattered, releasing an immense burst of energy that sent space-time hurtling outward. This isn't just poetic analogy. The math shows that such phase changes in quantum fields can generate exponential expansion, with the universe's fall from symmetry creating the very fabric of reality we now inhabit. Now, the James Webb Space Telescope is hunting for clues in the cosmic microwave background's faintest whispers. If inflation was driven by symmetry breaking, it should have left telltale imprints, subtle swirls in the polarization of ancient light, like fingerprints on a frosted window. Earlier telescopes glimpsed hints of these patterns, but JWST razor-sharp infrared vision could finally settle the debate. Even more tantalizing are the telescope's observations of ultra-distant galaxies, which appear oddly mature for their age. Some theorists argue this could signal a slower, more structured inflation process, one where symmetry unfurled in distinct stages rather than a single chaotic burst. Critics counter that inflation is already a flexible theory able to explain almost any observation by tweaking parameters. But the symmetry-breaking hypothesis offers something radical, testable predictions. If confirmed, it would mean the universe's explosive birth wasn't a random accident, but the inevitable outcome of deeper mathematical harmonies. The same symmetries governing quarks and black holes might have literally shaped the cosmos from nothingness. The implications ripple outward. If symmetry breaking triggered inflation, it could explain why the universe appears so finely tuned for life. The forces, particles, and even the dimensionality of space might all be relics of that primordial moment, frozen into place when the cosmic dice fell. Future gravitational wave detectors could listen for echoes of this event in the universe's oldest vibrations, while quantum simulators might recreate microcosms of symmetry breaking in labs. This isn't just about rewriting cosmology textbooks. It's about uncovering whether the universe's grandest structures, galaxies, clusters, the cosmic web itself are the aftermath of a single, symmetrical heartbeat. And if we're right, the next great revelation won't come from staring at the night sky, but from decoding the hidden mathematics that first set it alight. Crushed under the weight of a dying star's collapse, neutron stars aren't just cosmic oddities, they're nature's most precise sculptors. Imagine taking the entire mass of our Sun and compressing it into a sphere the size of Manhattan. The gravitational force would be so intense that mountains on its surface couldn't rise taller than a millimeter without crumbling under their own weight. This extreme environment doesn't just create density, it forges perfection. Measurements from pulsar timing reveal that some neutron stars deviate from perfect sphericity by less than 1 part in a million, making them rounder than the finest man-made ball bearings. What's truly baffling isn't just their shape, it's what that smoothness implies about the fundamental forces holding them together. Neutron stars are essentially giant atomic nuclei, bound by the strong nuclear force that normally operates over distances smaller than a proton. Yet here, this force scales up to stellar proportions without losing its precision, like a watchmaker's gear somehow maintaining perfect time even when blown up to the size of a city. This suggests the strong force might obey symmetries we've never detected in earthbound particle colliders, symmetries that only reveal themselves under pressures so extreme they warp the very fabric of matter itself. The secret could lie in quark-gluon plasma, the exotic state of matter where protons and neutrons melt into a soup of their constituent particles. Under normal conditions, quarks are perpetually confined within protons, but in a neutron star's core, they might break free and reorganize into crystalline patterns or superconducting fluids, structures so symmetrical they counteract any microscopic imperfections. Picture a snow globe shaken with unimaginable force, where every flake settles into flawless alignment instead of chaotic scattering. That's the level of order we're talking about, a self-correcting symmetry built into the quantum rules themselves. Astrophysicists are now using gravitational waves to probe these stellar spheres with unprecedented precision. When two neutron stars collide, the ripples in space-time carry subtle fingerprints of their pre-impact shapes. Initial data from LIGO and Virgo detectors already hints at deformations smaller than theoretical models predicted, as if some hidden mechanism is sanding away any asymmetry before the final crash. This could mean neutron stars aren't just symmetrical by accident, they're actively enforcing symmetry, like a cosmic version of a liquid droplet minimizing its surface tension into a perfect sphere. The implications stretch far beyond stellar curiosities. If we can decode the symmetries governing neutron stars, it might revolutionize our understanding of nuclear physics here on Earth. Fusion reactors, for instance, struggle with plasma instabilities that break confinement problems that neutron stars seemingly solved billions of years ago. There could even be connections to quantum computing, where maintaining coherence against decoherence mirrors the way neutron stars resist gravitational distortion. But the most profound revelation might be philosophical. In a universe often defined by chaos and entropy, neutron stars stand as cosmic monuments to order, proving that even in the most violent environments, symmetry doesn't just endure, it thrives. They're not just dead stars, they're masterpieces sculpted by laws we're only beginning to glimpse, written in a language of perfect geometry older than time itself. Every time you look at your hand, you assume it's solid, a fixed, classical object obeying the tidy rules of Newtonian physics. But zoom in close enough, and that solidity dissolves into a swirling quantum soup where particles exist in multiple states at once, where your hand could theoretically be in two places simultaneously. So why don't we see this chaos? Why does reality appear so stubbornly normal when the quantum underpinnings suggest it should be anything but? Enter quantum Darwinism, the radical idea that the universe isn't just generating possibilities, it's curating them, using symmetry as its selection filter. At the heart of this theory lies decoherence, the process where quantum systems lose their weirdness by interacting with their environment. When a particle's wave function collapses, It's not some mystical observer that forces the issue. It's the relentless ping-pong of photons, air molecules, and even cosmic rays that measure the system into a single state. But here's the twist: not all states are created equal. Some configurations, particularly those with high symmetry, survive this interaction marathon while others fade into oblivion. Picture a choir singing in perfect harmony versus one where every voice is off-key. The symmetrical version doesn't just sound better, it's literally more stable, drowning out the dissonance through sheer mathematical elegance. This isn't just philosophy. Experiments with quantum dots, nanoscale crystals that behave like artificial atoms, show that certain electron states persist far longer than others when bombarded by environmental noise. These preferred states often align with symmetries in the crystal's structure, as if nature has a built-in bias for order. It's like shaking a box of Legos and finding they've spontaneously assembled into a perfect pyramid every time. Quantum Darwinism takes this further, arguing that the states we perceive as real are simply the ones robust enough to leave copies of themselves everywhere, imprinted on the environment like footprints in wet concrete. Your coffee cup looks like a cup because its quantum configuration has been endlessly replicated by photons bouncing off it, while the zillions of other possible configurations vanish unrecorded. The implications are staggering. If true, this means symmetries aren't just aesthetic features of the universe, they're the scaffolding of observable reality. The reason we don't see Schrödinger's cat both dead and alive isn't because the universe forbids it, but because the symmetrical, classical outcome has been selected by environmental interactions, its information broadcast so widely it becomes inescapable. Even Time's arrow might owe its existence to this process. The past feels fixed because its quantum states have been irreversibly etched into the environment, while the future remains fluid, a sea of possibilities not yet winnowed by decoherence. Critics argue this merely kicks the can down the road. Why does symmetry have this privileged role? Some theorists point to the mathematics of quantum information. Symmetrical states require fewer bits to describe, making them computationally cheaper to maintain. Others suggest it's tied to the holographic principle, where the universe's information budget favors efficient, low-entropy arrangements. Whatever the reason, one thing's clear: the world we experience isn't the only one possible. It's just the one that's been ruthlessly optimized by quantum Darwinism, a cosmic survival of the fittest where symmetry isn't just beautiful, it's the law. So next time you marvel at the stability of everyday objects, remember, what you're seeing isn't the universe's full palette. It's the exhibit curated by an invisible hand, where symmetry is both the artist and the critic, painting reality stroke by stroke with quantum brushes we're only beginning to understand. String theory has always been the wild dreamer of physics, proposing that the universe hums with not just 3 spatial dimensions, but 6 or 7 more tiny, curled-up realms hidden in every point of space like invisible origami folds. For decades, these extra dimensions seemed like mathematical fairy tales, too small to ever detect. But now, a groundbreaking shift is underway. Researchers are uncovering that these hidden dimensions might not be passive spectators. They could be actively shaping the cosmos through symmetrical patterns so precise they'd make a snowflake look haphazard. Imagine space as a vast ocean with our familiar 3 dimensions as the surface waves. Beneath those waves, there's an entire world of microscopic currents, the extra dimensions twisting in intricate loops smaller than an atom. What's astonishing is how these loops might vibrate. Just as plucking a guitar string produces musical notes, these curled-up dimensions could resonate with quantum-scale harmonies, each vibration corresponding to a different particle or force. An electron might be one note, a photon another, all arising from the same cosmic instrument. The symmetries governing these vibrations wouldn't just dictate which particles exist. They'd determine how those particles interact, why gravity is so weak compared to other forces, even why the universe has the exact number of dimensions we observe. Recent mathematical breakthroughs have revealed something even more startling. These dimensions might not be entirely hidden. Under extreme conditions, like near a black hole's singularity or during the universe's first moments, their influence could leak into our reality. Some models suggest that dark matter, that elusive substance outweighing visible matter 5 to 1, might actually be ordinary matter stranded in a parallel dimension, its gravity bleeding through the dimensional barrier like sound through a wall. Others speculate that the inexplicable lightness of the Higgs boson could be a side effect of symmetrical cancellations across dimensions, as if the particle's mass is being tugged in opposing directions by unseen forces. The most tantalizing clue comes from the Large Hadron Collider. In 2016, a fleeting anomaly appeared in proton collision data, a slight excess of energy that vanished as quickly as it emerged. Some theorists argue this could have been a particle momentarily bridging our dimension with a higher one, like a fish breaching the ocean's surface. While inconclusive, such hints have sparked a new wave of experiments. Future colliders, like the proposed Future Circular Collider, could probe energies high enough to directly excite these hidden dimensions, potentially unraveling their symmetrical blueprints. But here's the real mind bender. If these dimensions exist, they might not be static. They could breathe, expanding and contracting in sync with the universe's expansion, their symmetrical vibrations fine-tuning the cosmos like a cosmic metronome. This could explain why the vacuum energy, the mysterious force driving the universe's accelerated expansion, is so bafflingly small. The extra dimensions geometry might naturally cancel out much of this energy, preserving the delicate balance needed for galaxies and life to form. Critics argue that without direct evidence, extra dimensions remain elegant speculation. Yet the math keeps pulling us deeper. Certain string theory solutions now suggest these dimensions could be arranged in Calabi-Yau shapes, complex, multi-dimensional geometries with symmetries so rich they could encode the entire standard model of particle physics in their folds. Picture a labyrinth where every turn reveals a new law of nature, written in angles and curves too precise for chance. Whether these dimensions are ever confirmed, their theoretical elegance is undeniable. They represent a universe where symmetry isn't just a feature, it's the architect weaving space, time, and matter into a tapestry far grander than we can see. And if we're right, then every law of physics, every particle, every force might just be the shadow of something vaster, a symphony played in dimensions beyond our own, waiting for us to learn how to listen. After 27 revelations peeling back the layers of cosmic symmetry from fractal space-time to quantum entanglement, from black hole holograms to vibrating higher dimensions, we arrive at the most ambitious idea of all. What if every pattern, every force, every law we've uncovered is just a fragment of one monumental symmetry, a single equation so elegant it could fit on a T-shirt yet profound it contains the blueprint for reality itself? This isn't science fiction. It's the cutting edge of theoretical physics, where researchers are piecing together clues that the universe might not just have symmetries, but be symmetry, a perfect mathematical object playing out in 4 dimensions or 10, or 26 like a shadow cast by some higher dimensional perfection. Take the standard model of particle physics, our best map of the subatomic world. At first glance, it's a messy collection of particles and forces, like a disassembled watch with gears strewn everywhere. But look closer and patterns emerge. The electromagnetic and weak nuclear forces unify at high energies, quarks and leptons arrange into neat generations, and even the Higgs boson's mass hints at cancellations between symmetrical partners we've yet to discover. These aren't accidents, they're breadcrumbs leading toward a grander design. Some theorists, like those working with E8, Lie groups a mesmerizing 248-dimensional shape, believe all particles could be vibrations of this single geometric structure, their properties dictated by how they intersect its symmetries. Picture a wind chime where every note is a different particle, and the chime itself is the master symmetry resonating across existence. The hunt for this unified symmetry isn't just about tidying up equations. It's about solving cosmic mysteries that have defied explanation for generations. Why, for instance, does gravity seem impossibly weak compared to other forces? In a master symmetry framework, gravity's feebleness might not be a flaw but a clue, a sign that it's leaking into extra dimensions or diluted by symmetrical cancellations we don't yet understand. Even dark energy's bafflingly small value could make sense if it's the residual hum of a symmetry broken during the Big Bang, like an echo of that primordial perfection fading across billions of years. But the most electrifying possibility, this master symmetry might not be static. Just as ice crystals form when water cools, the laws of physics we know, the four forces, the particle zoo, even the speed of light, could be the frozen remnants of a hotter, more symmetrical early universe. As the cosmos expanded and cooled, that pristine symmetry shattered like a pane of glass, leaving behind the fragments we now study in colliders and telescopes. If true, it means the universe isn't just governed by symmetry, it's an artifact of symmetry's unraveling, a cosmic tapestry still bearing the creases of its original, flawless fold. Critics argue that without experimental proof, such ideas remain beautiful speculation. Yet the math keeps delivering eerie consistencies. String theory's Calabi-Yau manifolds, for instance, generate particle properties with uncanny accuracy when their symmetrical shapes are tweaked. Even the masses of quarks and electrons, which seem arbitrary, can emerge from symmetrical relationships in these models, like overtones in a vibrating string. And if the Large Hadron Collider's next run detects supersymmetric particles, the hypothetical twins predicted by these frameworks, it would be the strongest hint yet that nature's deepest layer isn't complexity, but simplicity writ large. So where does this leave us? If a master symmetry exists, it wouldn't just unify physics, it would redefine our place in the cosmos. We'd no longer be accidents in a chaotic void, but participants in a grand, symmetrical dance older than time. Every star, every atom, every thought would be a note in a symphony composed in a key we're only beginning to hear, and the most humbling thought of all. The equations we're chasing might not be human inventions at all, but glimpses of a truth the universe has known since its first flawless moment. From the fiery symmetry of the Big Bang to the holographic order of black holes, we've traced 28 revelations that rewrite what we thought we knew about reality. Each one peels back another layer of the cosmos, exposing a hidden architecture more intricate and mathematically flawless than we ever dared to dream. But here's the exhilarating truth: we're not just passive observers in this grand design. Every equation we crack, every anomaly we measure, is a step closer to the ultimate revelation that all these symmetries, fractal space-time, entangled particles, vibrating higher dimensions, might be threads of a single, unifying pattern woven into the fabric of existence itself. Think of it like standing before an endless mosaic. At first glance, you see scattered tiles, a spiral galaxy here, a quantum fluctuation there, but as you step back, connections emerge. The golden ratio in a sunflower mirrors the spin of a black hole. The harmonics of neutron stars echo the vibrations of strings too tiny to see. Piece by piece, the fragments align, revealing a portrait of the universe where nothing is truly separate, where every law and force speaks the same symmetrical language. This isn't just beautiful, it's transformative. It suggests that the chaos we perceive might be the shadow of an order so profound, it redefines what reality even means. What comes next? The hunt for this master symmetry is already underway. Next-generation telescopes will scan the cosmic microwave background for whispers of primordial patterns. Colliders like the Future Circular Collider aim to recreate conditions so extreme, they might momentarily stitch the fractured forces back into unity. Even AI is joining the quest, sifting through data for hidden connections no human mind could spot. The goal isn't just to fill textbooks, it's to glimpse the universe's original blueprint, the equation that birthed everything from quarks to quasars. But here's the most humbling thought of all. If we're right, if symmetry truly is the universe's foundational language, then every breakthrough isn't just a human achievement. It's the cosmos remembering itself, recognizing its own reflection in the mirror of our curiosity. So whether you're a physicist, a stargazer, or just someone who marvels at the night sky, remember, you're part of this story. The next revelation could come from a lab, a telescope, or even a comment thread where minds collide like particles in a detector. If this journey through cosmic symmetry sparked your imagination, hit like, subscribe, and join the conversation below. What revelation surprised you most? Where do you think the next breakthrough will come from? The universe has kept its secrets for 13.8 billion years, but with every question we ask, every mystery we solve, we're not just exploring the cosmos. We're helping it unfold.